8B/10B encoding is a line coding technique used in the physical layer of certain Ethernet standards, notably Gigabit Ethernet, or 1000 base X over fiber, that maps 8-bit data words into 10-bit symbols for transmission. This encoding scheme adds a 25% overhead. 8 bits become 10 bits, resulting in a 1 Gbps data rate requiring a 1.25 Gbps line speed. Purpose and benefits. The primary reasons for using 8B/10B encoding are to ensure reliable data transmission over physical media such as copper or fiber optic cables. DC balance, DC free signal. The encoding ensures that the number of ones and zeros transmitted over time is nearly equal. This prevents a net direct current, DC, voltage buildup on the line, which is essential for technologies that use transformer or capacitor coupling, like standard Ethernet twisted pair or optical receivers. Clock recovery, the code guarantees a sufficient number of transitions, changes from 0 to 1 and vice versa, in the data stream, with no more than 5 identical consecutive bits, a bounded run length. These frequent transitions allow the receiving device's clock recovery circuit, PLL, to stay synchronized with the incoming data stream. Error detection, by using only a subset of the 1024 possible 10-bit symbols to represent the 256 possible 8-bit data bytes, the scheme creates illegal code combinations. The receiver can immediately detect a single bit error if an invalid 10-bit symbol is received. Control signaling, K symbols. The unused 10-bit patterns are leveraged as special control characters, called K symbols. These are used for low-level link management functions, such as signaling the start and end of frames, indicating link idle status, or aiding in byte synchronization, using comma symbols like K28.5. How it works. The 8B/10B encoder functions by splitting the 8-bit input byte into two sub-blocks, a 5-bit portion and a 3-bit portion. These are encoded using lookup tables into a 6-bit and a 4-bit output, respectively, which are then concatenated to form the final 10-bit symbol. The encoder maintains a running disparity, a count of the difference between ones and zeros sent so far. For input combinations that have two possible 10-bit output codes, one with more ones, one with more zeros, the encoder selects the version that helps balance the overall DC level of the signal. Usage in Ethernet. 8B/10B encoding is a hallmark of Gigabit Ethernet, 1000 base X, over both fiber optic and some copper links. However, due to its 25% bandwidth overhead, higher speed Ethernet variants like 10 Gigabit Ethernet, 10 base R, typically use more efficient encoding schemes, such as 64B/66B encoding, which has a much lower overhead of approximately 3%. In 8B/10B encoding, DC balance is the goal, a long-term equal number of ones and zeros transmitted, while running disparity, RD, is the mechanism used to track and control this balance dynamically. Understanding disparity and DC balance. Disparity of a symbol, the disparity of any 10-bit symbol is the count of 1 bits minus the count of 0 bits. The 8B/10B code ensures that every encoded 10-bit symbol has a disparity of either +2, -2, or 0. Running disparity, RD. The running disparity is a running tally of the cumulative disparity of all previously transmitted symbols in the stream. It essentially tracks whether there has been an excess of ones or zeros up to that point. The running disparity at the end of any symbol is always limited to two states, +1 or -1. DC balance, maintaining a bounded RD ensures that the overall signal is DC-free, AC coupled compatible. Without this balance, a long string of consecutive ones or zeros could build up a net DC voltage on the transmission line, example Ethernet's transformer coupled twisted pair, potentially causing signal errors and making clock recovery difficult. How running disparity, RD, achieves DC balance. The encoder uses the running disparity to intelligently choose between alternative encodings for the same 8-bit data. 1. Dual code options. Many 8-bit data words, specifically those that would result in a non-zero disparity if only one 10-bit output was available, have two possible 10-bit encodings in the lookup tables. One version has a positive disparity, example +2. The other version is the bit inverted version and has a negative disparity, example -2. 2. The encoder's decision. Before transmitting a 10-bit symbol, the encoder checks the current running disparity. If the current RD is negative, meaning there have been slightly more zeros than ones overall, the encoder selects the 10-bit code with a positive disparity, +2, to balance the count. The new RD then becomes positive, +1. If the current RD is positive, the encoder selects the 10-bit code with a negative disparity, -2, to compensate, and the new RD becomes negative, -1. If the chosen 10-bit code has a neutral disparity, 0, the running disparity remains unchanged. By alternating between positive and negative disparity codes based on the historical imbalance, the encoder ensures the long-term average ratio of ones to zeros remains at 50%. This bounded, continuous balancing act is how 8B/10B achieves DC balance. In 8B/10B encoding, control and special characters, formerly known as K symbols or comma characters, work as a separate set of 10-bit symbols that transmit information about the link status or frame structure, rather than user data, D symbols. These characters are essential because they provide a way for the physical layer hardware to manage the link without interfering with the network layer's data stream. Key aspects of K-symbols. 1. Distinct encodings. K-symbols use specific 10-bit patterns that are reserved and distinct from the patterns used for the 256 standard data bytes. The receiver is designed to recognize these unique patterns immediately. 2. Maintaining DC balance. Just like data symbols, K-symbols are carefully selected to ensure they also maintain DC balance using the running disparity mechanism described previously. They exist in both positive and negative disparity versions, allowing the encoder to switch between them as needed. 3. Synchronization. Detect one particular K-symbol, known as K28.5, is crucial for synchronization. This character is designed with a unique sequence of bits, example a comma pattern, that is highly unlikely to occur in the normal data stream. The receiver hardware actively scans the incoming bit stream for this specific pattern to determine the correct byte boundary, deciding where one 10-bit symbol ends and the next begins. Common uses of control characters. K-symbols are used for several low-level signaling purposes in gigabit Ethernet. Start/end of frame. K-symbols are used to delimit the boundaries of data packets. For example, a specific sequence of K-symbols indicates the start of an Ethernet frame, the start of frame delimiter. Link status and idle. When there is no data to transmit, the link continuously sends specific K-symbols, often called idle characters, to keep the physical link active, maintain DC balance, and ensure clock recovery circuits remain locked onto the signal. Error indication. Specific K-symbols can be transmitted by the receiver back to the transmitter to indicate that a physical layer error occurred, example an invalid data symbol was received. By having a dedicated set of non-data characters that follow the same encoding rules, the 8B/10B scheme allows for robust, self-synchronizing communication at the physical layer while ensuring a DC balanced signal. 8B/10B encoding and similar, more efficient methods are used in the physical layer of various Ethernet standards to ensure signal integrity and reliable clock recovery. 8B/10B encoding usage. 8B/10B encoding is primarily associated with gigabit Ethernet standards, specifically those operating over fiber optic and some short-range copper connections. Ethernet standard speed media encoding 1000 base SX/LX/ZX1 Gbps fiber optic. 8B/10B 1000 base CX1 Gbps copper Twinax. 8B/10B 10 base LX4 10 Gbps fiber optic, 4 wavelengths. 8B/10B, per channel, 10 base CX4 10 Gbps copper Twinax. 8B/10B, per lane, the 1000 base T standard, gigabit Ethernet over standard Cat5/5E/6 twisted pair copper cable, is a notable exception. It uses a different, more complex encoding scheme, PAM5 signaling with a scrambler, to achieve its speed over 4 pairs of wires. Without the 25% overhead of 8B/10B. Similar methods, higher speeds. As Ethernet speeds increased, the 25% overhead of 8B/10B became too inefficient. More recent, higher speed standards use more efficient encoding schemes that combine scrambling with larger block sizes. 64B/66B encoding. This method adds only 2 bits of overhead to every 64 bits of data, an efficiency of over 97%, approximate 3.125% overhead. It is the standard for most modern high-speed Ethernet variants. 10 gigabit Ethernet, example 10 base SR, 10 base LR, 10 base T, 40 gigabit Ethernet, 100 gigabit Ethernet and higher speeds. 128B/130B encoding. This scheme further reduces overhead to about 1.54% and is primarily used in high-speed interconnect protocols outside of Ethernet, such as PCI Express 3.0 and later generations, as well as USB 3.1. Decoding on the receiver's end in an 8B/10B encoded system involves a multi-step process that reverses the encoding procedure while monitoring the signal for integrity and synchronization. The process happens at the physical layer, PHY, hardware, 1 clock recovery and synchronization. The very first step is for the receiver to synchronize its internal clock with the incoming data stream. The frequent transitions guaranteed by 8B/10B encoding allow the receiver's phase-locked loop, PLL, circuit to lock onto the signal and reliably sample each individual bit at the correct time. 2 byte alignment, detect. Once bit synchronization is achieved, the receiver must determine where each 10-bit symbol begins and ends. This is the byte alignment process. The receiver continuously shifts its 10-bit sampling window across the incoming bit stream, checking each potential 10-bit sequence. It specifically looks for the unique, unmistakable pattern of the K28.5 control character, the comma symbol. When the comma pattern is detected, the receiver knows it has found the correct symbol boundary and locks its alignment to that sequence. 3. Disparity management. The receiver also tracks the running disparity, RD. It uses the first bit of each incoming 10-bit symbol to check the cumulative disparity. This confirms that the encoder on the other end maintained DC balance correctly and helps validate the integrity of the received data. For 10B to 8B conversion, decoding, each aligned 10-bit symbol is passed to the decoder. The 10-bit symbol is looked up in the receiver's internal 8B/10B lookup tables. If the symbol matches a valid data symbol, D symbol, or control symbol, K symbol, the decoder outputs the original 8-bit data byte and updates its internal running disparity counter. 5. Error detection. A critical function of the decoder is error detection. If the incoming 10-bit pattern does not exist in the valid lookup tables, an illegal code, the receiver immediately knows that a transmission error, example a single bit error caused by noise, has occurred. The device flags this error, often by sending a specific error K symbol back to the transmitter or logging it internally, and typically drops the entire current frame. Summary. The receiver's role is essentially to listen for the link synchronization signals, K symbols, align the bytes correctly, check for errors using the valid code rules and disparity checks, and reverse the lookup table process to retrieve the original 8-bit data stream. In an Ethernet system using 8B/10B encoding, the transmitter and receiver cooperate closely at the physical layer, PHY, to ensure data is transferred reliably, synchronized, and with proper signal characteristics. What the transmitter does. The transmitter is responsible for converting the digital data provided by the upper layers into a robust electrical or optical signal suitable for transmission over the physical medium. 1. Encoding. It takes 8-bit data bytes, D symbols, or control information, K symbols, and uses a lookup table to convert them into corresponding 10-bit symbols. 2. Disparity control. It tracks the running disparity, RD, and dynamically selects between two possible 10-bit codes to maintain DC balance in the outgoing signal. 3. Synchronization signaling. It inserts K symbols, like idle codes or start-of-frame delimiters, into the stream to manage the link and help the receiver establish alignment. 4. Serialization. It converts the parallel 10-bit symbols into a single, high-speed serial bit stream. 5. Transmission. It drives the physical signal onto the cable or fiber optic link at the required line rate, example 1.25 Gbps for gigabit Ethernet. What the receiver does. The receiver is responsible for detecting the incoming signal, restoring synchronization, reversing the encoding process, and verifying data integrity. 1. Clock recovery. It uses a phase-locked loop, PLL, to extract the timing clock from the transitions present in the incoming bit stream. 2. Byte alignment. It scans for the unique comma pattern, K28.5 symbol, to correctly align its internal framing to the 10-bit symbol boundaries. 3. Deserialization. It converts the high-speed serial bit stream back into 10-bit parallel symbols. 4. Decoding. It uses a lookup table to decode the 10-bit symbols back into the original 8-bit data or control information. 5. Error checking. It monitors the running disparity and checks for invalid 10-bit code patterns. Any invalid code immediately flags a transmission error. 6. Data forwarding. It passes the verified 8-bit data up to the Media Access Control, MAC, sublayer for further processing.